안녕하세요. 영어 강의에 대한 교무처에서 이제 영어 강의에 대한 이제 이 주의사항이 전달이 됐어요. 그래서 학생들은 영어 강의를 의무적으로 이제 또 이수를 해야 되는데 영어 강의 A거든요. 이 벡터 캘큘러스가. 근데 영어 강의 A인데 저희가 그래서 그 교재라든지 텍스트는 전부 영어로 돼 있고요. 근데 이제 제가 그 교수자가 영어로 강의를 하지 않는 부분에 대해서 혹시나 여러분들이 또 이의를 제기할 수도 있을 것 같아서 제가 높아심에서 오늘부터는 이제 영어 강의를 하려고 합니다. 조금 제 발음이 부정확하거나 원어민 발음이 아닌 영어를 구사하더라도 여러분들의 넓은 그 해량으로 좀 좋게 봐주시길 바랍니다. So, from this week, I will speak in English, and our lecture will be English speaking course, and so this is option A in when you take the courses. It's mandatory to take two English speech courses, and this is one of the option that we provide English textbook, and also we speak in English in the lecture. So I will cover the topics now by explaining things in English. Okay, so please be careful. And okay, so now I want to cover this surface integral in today, and also we review the last week's definition of the parameterized surface. So recall that this parameterized surface is that actually a map, okay, a map from a domain in R2 in the plane to the image in R3, okay. So we have a domain. So let's look at the iPad. So we have a domain in all two planes. So let's say this B and U as the two parameters, and so this is U comma B as one point here. Let's say small p, and then from domain D that we have an assignment. It's called phi to the space, right? The space in P, large P, let's say x comma y comma z. Okay, so this is z and x and y. All right, so this all the points in the domain here is imaged. So now we have some collection of the points, and if phi is continuous, then this whole part of D is mapped to this continuous image. Right? So it's image, actually the image of this, we can say it's a surface. Okay, so this is surface. And in this case, this is called the parametrized surface. Okay, parametrized surface. So if you think about this, any surface, let's say, if you think about cylinder or sphere, these are called surface too. But if we cannot find the parameterization of this surface, we do not call them parameterized surfaces. Okay, in cylinder case, we know there is a parameterization. So there is a map from a domain in R2 to this surface, right? So we actually found the parameterization in the example. So we call that so this using the cylindrical coordinates, right? So this all cosine theta and r sine theta and comma z, right? And this r is fixed. Let's say this is r0 fixed. Then this is just two parameter, and this is theta and z, right? So we know there is a parameterization for this cylinder, and cylinder is now, it's called the parameterized surface. And again, and this sphere case, we know that if the rho, this radius of the sphere is fixed, let's say rho 0, okay. In this case, we know that spherical coordinate is give rise to a parameterization of the sphere. Okay, so we say that the sphere is also parameterized the surface. So these examples are well known, and most of cases we know that everything's are parameterized case. So for example, that when you have a graph of the function, let's say z equal fxy. So when you are given this z equal fxy case, this is always what? This is always parameterized surface by this canonical parameterization, putting this xy comma to xy in fxy, right? So this we call this canonical parameterization. I'm putting this here denote f, right, which is induced from f. So these are these parameterized surfaces. So last time we actually covered this definition and then how to get the tangent plane. But to get the tangent plane, if you remember, this tangent plane is determined by these two linear vectors in which is tangent vectors, and that was so given a parameterization, say phi, right? We get the important vector from this phi that say this p sub u and p sub b, okay? Which is which of each of which is what? A directional derivative, okay? So this is directional derivatives. Basically tangent vectors, okay? Tangent vectors. So if they are linear independent, okay? If they are linear independent, or this cross product of this pi u and pb is not zero, then we say that this p sub u and p sub b and linearly independent. Okay, and we know that these two vectors generate a tangent plane. Okay, so tangent plane is actually two-dimensional case, and two-dimension means that they have a two generators, and that means that any vectors is combination of linear combination of this vector pi u and pb. Okay, pb, pu, and pb, and so pu and pb is linear independent, and it generate this set generates what? Generates any vectors in the tangent plane, and tangent plane is also determined by the vertical vector. So we know that there's any in space in R3, there's a tangent plane has the form that a x minus x0, and b y minus y0, and c is z minus z0 is equal to 0. That means that this is equal to what? This is equal to some point p0 here, that x0, y0, and z0, and which is normal vector. We need normal vector, that there's a normal vector n here, right? And any other vector is here, x, comma, y, comma, z. Okay, that's any p. So this means that p minus p0 vector, okay, this vector is perpendicular to normal vector, okay? And that is another saying is inner product is equal to 0. So normal vector, take the inner product with this p0 vector, which is what? X minus x0 and y minus y0 and z minus z0, and normal vector is now a comma b comma c. Okay, so we need this normal vector, but the normal vector is now decided by what? This is p, so this is p sub bu, cross product is p sub b. This is one of the normal vectors, and we say that this is large N, right? And the small n is given by what? By dividing the size of the vector. So let's say, so this is unit vector, and psi u times psi b divided by the size of that vector, or just n divided by the size of the n. Okay, so this is called outward normal vector. Okay, so this is unit normal vector. Okay, so one of the normal vector. And also we have an opposite side, opposite direction, that the plus and minus sign. So later I will explain that how to determine the this plus or minus sign. But anyway, we need to be consistent with the sign. So once you choose the plus sign as an outward direction, then we just keep that direction, okay? And also at the beginning, if you think that this opposite side is outward, I mean, you can always decide which is the inner side and which is the outer side. So when you decide inner and outer side, then by taking this normal vector, okay, normal vector direction. So normal vector direction is actually determining that this outgoing or inward and outward. So this was needed for determining that tangent plane. Okay, so last time we just covered at this point. And also one thing, if you remember, that we actually explained that surface area element, right? Surface area element, so-called ds, right? So this is ds is actually surface area element. So, and also we have a bold s. We have a bold s here. We have a bold s. I say this is bold s. So this is bold, or yeah, I can actually make it thick. Yes, or this vector notation. This ds vector is what? This is. So this was actually combining normal vector. Okay, so we just putting the vector is representing this quantity, the scalar and direction, right? So we need this quantity as ds. This is quantity ds, right? And so the size of this vector is ds, right? And what about the direction? Direction is normal vector direction. So this normal vector and ds. So this is vector notation. Okay, so this is vector notation, and we are going to use this vector notation soon. Okay, to define this surface integral. So now let's come back to this our note here. Let's look at that. So I will define the surface integral here. Look at the definition. So when you have a parameterized surface sigma and a function defined on the sigma, then we can actually define this integral of f over sigma. Okay, so this is the notation here that this is surface area element, right? So we only need surface area element in this case. So it's f ds, okay, over the sigma, surface sigma. Okay, so actually the surface is stand for the initially s as the first word, but in this case we are going to use the surface area element for the s, right? We already saved s for the surface area element. So rather using that s again, that we are now changing the surface for the sigma, okay? And this, what is the definition of this surface area, surface integral of the function f over sigma? That is actually, so everything moving to the two-dimensional case. Let's think about the picture, okay? Let's think about the picture, right? So let's look at the picture, and so here we have this function, right? We have this function defined on the surface sigma, right? So actually it's so at the point of here, let's say P, what we do is that this F, you just plug in large P at the point, right? I can say, so this, you just divide the surface by small pieces of the okay, you just get the small piece of the area, right? And then you choose one point here, let's say P. I can say P star, or you can choose, you can pick up the any point there, and then this small area, right? Small area, the time small area. You want to say that delta S, right? You want to say delta S, right? Delta S. And then you add up all these things in. Okay, take the sum, right? So this is surface area element. So this is, and if you take the limit, right? So you divide by here, you divide this one side and the other side, and you just make the division more finer and get the limit goes to 0, both areas. Then you get the limit of the integral, right? So you get the limit as an integral. So the limit is what? Over sigma, right? So real computation is happening that adding all these ingredients. But we can actually translate this quantity in terms of the domain, because of the we have the here P, and we have the domain here, right? Domain. So in domain, you just divide the domain. Okay, so this small part of domain is actually mapped to this small part. Alright? So this FP star is actually what? F small, let's say this is small p star, so this is f phi small p star. Okay, and then what's the small a here is the delta s, but delta s actually was done by these delta u times delta b. Okay, so delta u times delta b. So this delta u and this is delta u and delta b is also the rectangular area. But also we just have a change of rate. What was the change of rate of this area into this area? That was what? That was this normal vector large n. We needed the large n, right? We needed the large n. So that was the large n delta u delta v. Okay, and this was actually delta s. Okay, so we have this surface integral as now f ds is actually is the domain, as the domain was changed into the d, right? D and pi f u comma b, everything is in terms of u, right? I mean, also the area in the surface case, that it's the area of the rectangular region times rate of change, right? So this piece of u and piece of b, that was the rate of change times du dv. Okay, so this is actually the formula we need. All right, let's come back to the example. So I'm now saying that everything I explained this part here, that so the meaning of this integral. So this is very natural, and so you see that again you need parameterization to deal with this surface integral. Okay, basically you need to compute what? Compute always this normal vector large n, okay, and take the size of that. So let's take the example 3.2. 3.2 case that we have some graph of the function, okay, z equal x plus y squared on domain is rectangular region, right? 0, 1 times 0, 2. And the function is now given by fxy, fx, y, z is x times y, okay? So, and so we need to compute that this ds, right? So ds, and also this parameterization. So in this case, the natural canonical, so let's skip this. So then let's look at this canonical parameterization. So we have a g equal x plus y squares, right? So this is fx comma y type. So we have a canonical parameterization is x comma y to x comma y comma fxy, right? And in this case, normal vector p sub x times p sub y is given by minus f sub x I minus f sub y z plus k. So this was our computation before. So you remember in this case, I emphasized that this canonical choice of parameterization formula is worse to memorize. Okay, so actually in this case, f sub x now f sub x is 1 and f sub y is 2y, right? So yeah, that's okay. So we have minus I minus 2yz plus k as a normal vector. Okay? And the size of that is square root of square 1 and 2y square and 4y squares, and k in this case 1. So yeah. So we have this. So let's come back to the computation. So fxy was just xy, so we have an xy and square root of 2 plus 4y squared as the rate of change times the rectangular area. So dy or dx or dx dy. It's in Fubini theorem that in both dx dy or dy dx dy or dy dx is both available. And in this case, it's better to change that the order of the integration. So we do dx now, and then we do dy separately. Okay, so it's okay to. But I mean, what I'm saying is that we do the integration dy first. So if you do dy first, then this is only involving y, and this is typical problem of the substitution, right? So instead of 4y squared, then you just instead of the y squared and y squared, you just take the u equal y squares and dy. So this 2y dy is du and everything, you know, this is typical change. So I can actually compute and also once you compute this, then this is just a constant and just constant comes out and you do calculation about x, right? So this is not difficult, so we can compute. I hope that you complete this computation by yourself in after the lecture. All right. So now we covered that this surface integral case, and we now move to the this vector valued things in terms of this. So let's go back to the surface integral, and so. Okay, now we define this now the surface integral as here vector notation, using vector notation. Now, so when you have a vector field here, bold F is a vector field. So you have a vector field over sigma, then you can define surface integral of this vector field F over sigma as this. So what the quantity you have to integrate is that inner product between this vector field and this vector surface area element, right? So this vector surface area element. So this surface area element is bold symbol. This means that we have a vector, and this is quantity is ds surface area element, the size of the vector, but direction is normal direction, right? So actually we have to integrate this quantity f dot normal derivative n. So f dot n is scalar valued function. Okay? So this is okay to from the previous definition that f dot small n is scalar valued function, right? So this is associated with this previous definition. Okay? All right. So but let me think about this. But that large n was what? Large n gets this. Let me come back to this definition of the here. So this when you have given a vector field f, then actually we can actually define this. F dot n as a scalar valued function, right? This is scalar valued, right? And then surface area element. Okay, so this is what we are looking for. Okay, and but by the way, But if you remember this, the function integral over sigma, then this is equal to d, right? D, and this function, right, is combining phi, right, and this normal vector and du dv, right? So that was the computation. And so let's go ahead, and in this case that we know that n is already fixed, right? Once you define this parameterization. So this small n was actually large n divided by the size, right? So if you plug in back to the formula here, I think that it's not quickly yep. So now this image is slowing down. So because of the traffic, so please allow me to be a bit slow. All right. So yeah. So we can actually. So we have this large f. We're just putting the point psi u comma v, right? And then this normal derivative dot with normal derivative, and then we actually have the size of this ds, but ds is now the size of the large n times du dv. Okay, and that's domain of the u comma v is in D. So, and this is canceled out each other, and finally we have so this f phi sub u comma b dot and phi sub u times phi sub b and du dv. This is surface area. Surface not surface area, but the surface integral of this vector field f over sigma. Okay, so the sigma. So the physical meaning of this is actually important to us. Let's come back to the screen. Yep. So let's move down. Here I said that this is written is in red color, that the physically the surface integral of the vector field over sigma is what? It's a total flux of f through sigma. What was the total flux? Total flux is this the rate of the flow, right? Rate of the flow through the surface sigma. Okay, so whenever f, so in that case f stands for the velocity vectors of the fluids. That fluids moves from one side to the other. Then you see, you just compute how fast this flow actually get out of the surface. So that's the rate of change is total flux, right? So in the picture here, so let's come back to the picture. Yes, so we have a surface now, right? So we have a surface, and look at the normal vector here. So this is tangent plane, and this is normal vector, let's say. Okay, or just small n. But so we actually flow is not this way, but so there's a vector field large F. So what we need to compute is net amount. So the net amount, okay. So you see, the fluid flows in this direction. This does not go out, right? This does not go out, but actually every component does not contribute, but only the component which is in the same direction as normal derivative is flowing out, right? So every vector is decomposed into this normal component and orthogonal component, which is orthogonal to normal, right? So what we need is that this component. So this component is what we need, right? So this component, again, so let me put this. So this component is what we need, right? So this the component which is this in the same direction with normal is this component actually contribute go throughout the surface S at this point. So what we're computing is that actually this n component of this large F, right? So that's the what we are calculating in the surface area case, surface integral case. So we are actually computing the total flux, right, throughout this S, whole surface S. All right, so this is the physical meaning of this surface integral of the vector field through sigma or S. I say the sigma here. Okay, so let's come back to the file. And so let me compute this example. So think about this case that the flux, so we just compute, the example 3.4, we compute the flux of the vector field large F over the triangle consisting of vertices 1, 0, 0 and 0, 20 and 0, 0, 3. Okay, so let's think about the picture in the iPad. All right, think about this picture. That yeah. So we have the situation that here. So this P and Q R, and so this triangle. So this triangle is surface we are looking at, and that vector field is given. This vector field is given now. Let's come back, and this is x squares. Okay, x squares I plus yx z plus zx. Okay, so this was the vector field. So what we have to do first is that define the parameterization of this triangle, right? Otherwise, we cannot do anything. So if you remember this integral formula here, look at that. So if you look at this formula, that we need to find the parameterization. But this triangle is actually the part of the plane. So think about the part of the plane. So the plane is that the plane equation is, in this case, look at that, this x plus y over 2 plus 3 over z, g over 3 is 1, right? That's the plane. And if you look at the part of the plane, then we still keep the plane equation, but we only restricted to the domain, right? So we do not consider whole plane xy, but only triangle region, right? So only the triangle region. Let's come back to the iPad. So if you look at this S as a graph of the function, then we have the natural canonical parameterization. Say this triangle region is our domain, right? And we just decide the height there, then that's the canonical parameterization. So x comma y, and what was g? So the gk is the from plane equation that we can solve g in terms of an x and y. So what was that? So let's come back to the file. So g is now, right, g is equal to, right, that's 3i 3 minus 3x minus 3 over 2y, right? So this is equation we need for the canonical parameterization. And so that this is determined, this g is the height of the point, and which is determined by x and y. So we have two parameters in x and y. So we have a canonical parameterization. Again, this normal vector is given by, so f sub x minus f sub xi minus f sub yj plus k. So this is normal vector, right? So this is normal vector, and our fxy is now, if I remember, that 3 minus 3x minus 3 over 2 y. Right? So f sub x is minus 3 and f sub y is minus 3 over 2. Okay, so this normal vector is in this case, and 3i plus 3 over 2j plus k is this outgoing normal vector. Okay, so we've computed this, and what is that? Vector field. So the vector field in xyz case, that we just plug in xyz. So we only compute the g. Instead of g, we plug in back to the this 3 minus 3x minus 3 over 2y. Okay, so what's the f? Phi xy is x squared I and xyj plus xg is this, right? G is 3 minus 3x minus 3 over 2y and k. So let's come back to the computation. So right, so I finished this calculation. So this is normal vector, and this is a vector field over that point in terms of the parameterization. Right? Everything is in terms of the x and y now. So we just take this inner product between this f and n, right? So we just take this inner product. So this normal vector, and then we just calculate in dx and dy, right? So that's, if you remember, then this is what we this is what we do. Yes. So yeah, so we don't need this part, right? So we only need to compute and this inner product between f and large n. So I computed here that already. So if you look at that, the second part is already computed. Now it's the inner products, right? So if you take the inner product, and I can calculate then 3x squared plus here and 3 over 2 times y over x. And this, the last part, 3 minus 3x minus 3 over 2y times k, here component is 1. So this, and 3 over xy is cancelled out, and we have only 3x squared minus 3x plus 3, right? And then you just do integration only terms x, and x is regarded as a constant term. So if you do dy first, and then you just do the but remember, this domain is triangular region. So if you remember, this domain was the triangular region. Let's come back. So domain was the triangular. In this case, this 0, 0 to 0, 2, 0. So this, if you remember this things that you have y equal 2 minus 2x, right? So so you see that this is I'm sorry though. So this is something wrong. So if you remember this, yes, I was wrong. So in this computation I was wrong, and instead of this 2x plus 1, here instead of 2x plus 1, I think this is wrong, something wrong. This is 2 minus 2x, right? So this is 2 minus 2x and 2 minus 2x, then you just finish the calculation. So I was wrong in this upper limit, upper bound of this y. And actually, basically, I was wrong about this domain, right? So I was wrong here. But I think that I hope that you just fix it. And I want to emphasize that sometimes we need to consider that not only one piece of the surface, but we sometimes we need to consider that the surface which is itself is not parameterized, but each part of the pieces are parameterized. Let's say, for example, in the picture that you see. So if you combine two surface, right, and sometimes it's not that smooth because of it's not smooth surface, but let's say, think about this. So each piece is, so think about this case, right? So let's think about this. So we have one piece of the surface here, and then we put this another one, right? So this S1 and S2, okay? And along this line, let's say, along this line, we have now, it's not the smooth point, so it's not the smooth point. So think about that, this point, yep. So this is not the smooth. So it's not the regular surface whole together. So if you think about the S1 union of S2, this whole thing is not smooth or regular surface. So we cannot find the tangent plane at this point, for example here, but we can, when you try to compute this flux or this integration of the function over the surface, let's say this is sigma, whole sigma, then we can do separately. So we can compute S1 part and S2 part respectively, and then combine them together, right? So we can do calculation each piece and then add up. So we can do such things in integration. So that's okay. And in this example 3.5, example 3.5 explains that example. So let's look at this. So this is this cylinder picture, right? So when you have a cylinder and top and bottom, and this intersection part is not smooth, but we can actually we are okay to do things in separately. So we have the cylinder here. Top is the plane and the bottom is also plane, but the lateral side is what? It's a smooth, right? It's smooth. So there is no way to parameterize this cylinder, the whole thing as a top, including top and bottom. But we can actually, when you compute the total flux, then you can actually do the top and bottom and the lateral side respectively. So this is the point. And if, so this example 3.5 case that we need to explain the picture better. So think about this. So we have a cylinder. Yes, we have a cylinder. And our vector is actually what pointing out. So the cylinder is, if you think about this vector, there's some quantity I and some quantity j. There's no quantity in k direction, right? So there is no quantity in k direction means that the vector field is something like that. Okay, but this is parallel. This is something parallel to which is the direction is in xy direction, xy plane, but there's no component in k or z axis, right? So I was wrong in the picture here that there is nothing here, and so this vector field has no contribution to the this up. So in the top, if you take the outside, in which direction is this? Maybe outside, let's say k, this outgoing direction, and in bottom here, minus k is outgoing direction. Then what we need to calculate is the inner product between this normal derivative and f, but f and k, f dot k is 0 and f dot minus k is 0. So when you compute the total flux in this case, this contribution from top and contribution from bottom is 0. Okay? So we only compute this total flux case, that surface integral over f, in this lateral side. Okay, and lateral side in cylinder is now parameterized by what? Cylindrical coordinates. So everything is in cylindrical coordinates, and we can compute. We can continue to compute. So let's look at the comeback. Let's come back to the iPad, the screen and PDF file here. That so. Yeah, so we just have this cylinder, this radius 2 cylinder, and so we can parameterize using the cylindrical coordinates and x equal 2 cosine theta and y equal 2 sine theta and g equal g. So we only need two parameters, theta and z, right? And theta 0 to 2 pi, and g is what? 0 to 3. Okay, so top was g equal 3. So we have theta is from 0 to 2 pi, and g is 0 to 3, right? And we know the normal vector in this case, right? We know the normal vector in this case that if you have this, if you have this, that we have a normal vector is this, and also if you think about the size, that because of this x and y is in the circle, right? X y in the circle, that the size of this vector is 2, right? So the ds is 2 d zeta dz. And so if you compute this normal vector times f, we have xy I plus y squared j. Think about this, and dot with this xi plus yj and ds. Yes, so we have this x squared y plus y squared and ds. But if you think about the cylindrical coordinates, and instead of x and y, we're just putting this 2 cosine theta and 2 sine theta, and we have no z. That's a good point. And so g part is easily calculated, just the 3. And if you think about the d theta case, then you have a cosine square theta times 2 sine theta and sine square sine cube theta. So sine cube theta is not easy to calculate, but I hope that you can actually calculate this sine cube, right? So I think something, if you keep this calculation, let's say, so if you combine everything in here, that cosine square plus sine square and sine theta is common, all right. So you don't have to do separate terms each, but if you combine whole thing together, then if you have a here 8 cosine square theta and sine theta plus sine cube theta, but sine theta is common term, so if you factorize, then you have a cosine square plus sine square, which is 1, so you have a sine theta, and the integration of sine theta is just 0 over 0 to 2 pi. Yes. So this is the example which I wanted to show, and I know that it's the calculation is quite complicated procedure, and you're not familiar with this surface integral case. But as I emphasized, what we do first is to find the parameterization, and then to find the normal vector. Once you find the parameterization in normal vector, and you just this is just the easy calculation, right? But at the final point, you need some integration technique to finish this computation. So I must say that you have to master this integration technique to finish this computation. Okay, but in principle, to do a surface integral, you have to practice getting this parameterization of the several surfaces in, and then to find this normal vector, because of the, you have to do the product, right? Product of the outer product of the two vectors, which is involving this determine a 3x3 matrix element. Okay, so this, my explanation of the surface integral is done, and hopefully you just review this material again and again if you cannot understand at the first glance. But if you repeat to the calculation, then I think that you can actually get the precise meaning or precise sense of the surface integral. Alright, so see you next time.